Hello and welcome to the Daily Space for today, January 7th, 2019. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. Today we have both a very slow news day and a very fast news day. This is because today's news is about to come, but isn't really here yet. So I'm going to go over a couple of cool stories that arrived in my inbox. Then we're going to take a little break before going over live to coverage coming to us, or at least a press conference coming to us, from the 233rd meeting of the American Astronomical Society, which is taking place this week in Seattle, Washington. We will be bringing you all the press conferences as clearly as the internet allows, providing commentary and allowing you to ask questions. These press conferences are going to be occurring twice a day at 10:15 a.m. Pacific, which is 1:15 Eastern, and also at 2:15 Pacific, which is 5:15 p.m. Eastern. So stay tuned for all of the news, all of the time, all of it coming to you live as the internet allows. Now, for today's top stories, I have two quick news bits. The first one being new ideas on how to better capture distant imagery using space telescopes. Currently, there are a variety of different space telescopes, either in the process of being constructed or being dreamed about on paper by astronomers around the world. One of the things that does always leave astronomers a bit worried, however, is what do you do when the field of view of your telescope is so small that there are no bright stars in that field that your telescope can use to guide? The Hubble Space Telescope relies on an amazing catalog of guide stars, the Hubble Space Telescope Guide Star Catalog, to keep its pointings accurate as it explores the sky for us. In every field of view, there is at least that one object that its guide camera can grab onto to make sure that the telescope stays, well, with that brightest point on the same pixel at all times. With future telescopes, fields of view may be too small in order for this idea to work. New research out of the Massachusetts Institute of Technology, however, says we can do the same thing with space telescopes that we currently do with ground-based telescopes. That is, we can create artificial stars. Here on the surface of the planet, when our biggest and best telescopes want to accurately observe the sky, we often use artificial stars that are generated by lasers that excite upper levels in our atmosphere. The telescopes lock onto these laser beams and very carefully measure the fluctuations in shape of these artificial stars and flex the mirrors of the telescopes to compensate for whatever noise the atmosphere is introducing into the shape of these artificial stars. In space, we don't have the same problem with the atmosphere distorting stars, but we do have a problem of not having a solid base upon which to set our telescopes and make sure that the pointing stays steady. Without a ground, we need something else to hold on to. In this case, we hold on to the light of distant stars. When those stars aren't bright enough, well, it is suggested that perhaps we can use CanSats, CubeSats, small little spacecraft to point lasers at these massive space telescopes. Now, of course, the question arises, what exactly keeps these CanSats, CubeSats, whatever they turn out to be, properly positioned? Well, in this case, there's lots of different things that can take place because that's a dedicated platform. It can either be, well, constantly in one position so that turning a laser on and off is no big deal. So you have a constellation of these things in steady orbits. They're never getting moved. They're never moving themselves. They turn on their lasers, and their lasers simply, well, are stable because their orbit is stable. Another idea is perhaps you can stay in constant communications with them from the Earth in order to maintain their position. However it is done, it may be that these future little CanSats are the guiding lights that our space telescopes need. Now, in other news, we have dark matter on the move. Astronomers have long been trying to figure out just what are the various factors that affect dark matter. Dark matter is this, well, still mysterious stuff that is out there distributed among the stars and galaxies in ways that gravitationally move things around quite rapidly, but doesn't interact with the electromagnetic force in any way we've been able to discern. It doesn't give off light, it doesn't reflect light, it does gravitationally bend light, which is how we map out its position. Now, with dark matter, we do have the capacity to try and figure out via various means, such as where are stars located in inter-galaxy cluster space, where in galaxies do we see things moving at what velocities, through the motions of different objects, as well as through the bending of background light. We're able to map out the locations of dark matter in systems. Now, just as you can use intercluster stars to track out the position of dark matter in galaxy clusters, it's now being seen that you can use gas to map out the dark matter in galaxies. So, as we talked about, I believe it was last week, in galaxy clusters, there are stars that get stripped out of individual galaxies, and they settle into the gravitational distribution of pole of the distribution of the dark matter in these clusters. Well, with individual galaxies, instead of looking for the torn out stars, you look for the torn out gas. In the image that we have up here, what we see is a simulation of where hydrogen gas in a dwarf spheroidal galaxy should appear as a result of star formation heating up the system and pushing out the gas. Then we have real data showing the distribution of gas, which should be a function of both the heating and the dark matter location. And what we see is that the simulation where things are moved by heating is the same as the real observations, which indicates that the dark matter is also moving in response to the heating. Now, I haven't had time, because this is a brand new press release, to go through and read the science paper in detail. So I'm sure there's a lot of information behind this. We're going to work on bringing you all of these details in the days and weeks to come. But the key point here is we now know that dark matter can respond to thermal conditions. Its velocities can be increased. It moves in response to being heated up. This is a normal process for particles. You heat them up, they move faster. This is how gas works. Now we know it's also apparently, maybe, hopefully, paper needs to be read in detail, how dark matter works. So this is a cool new result. Now I have 5 minutes before the press conference at the American Astronomical Society meeting out in Seattle, Washington starts up. So I am going to quickly take a few of your questions. As always, if you can please at me with your questions, it will make it much easier for me to find them in the chat. Now, as always, The Daily Space is a production of the Planetary Science Institute working in collaboration with Youngstown State University. We are here to bring you the daily news most Mondays through Fridays, and to also bring you special events as they happen. Today, we're going to be bringing you news from the American Astronomical Society meeting live right here on CosmoQuest. In future days, you may see space launches, you may see spacecraft landings. Whenever it's streamed, we are here to answer your questions. Okay, so Larry Weird and Proud is asking, is heat an electromagnetic process? No, it is, it has to do with the motions of objects. So forces, in this case, it's conservation of momentum. It's actual collisions between particles. And that's kind of awesome. It's also the absorption and re-emission of photons in many cases, but here what we're talking about is collisional. So looking to see what else. So Paranor is, thank you for posting the links to the AAS meeting. So to give you highlights of what's going to be coming in the press conference that is about to start, we have talks on the disruption of the Orion. Thank you so much for the bits. We have disruption of the Orion molecular core by a massive star, the universal presence of night-side clouds on hot Jupiters, small transiting planet that was discovered by citizen scientists, and Spitzer spots a sixth sub-Neptune in K2 138. So Henny's Vorverp is asking, is the dark matter being hit by itself, or is it colliding every now and then with something else? I don't know. These are the things that I need to learn more about. Astro YYZ is asking, how do the CubeSats maintain their positions relative to the telescope? So the easiest way to do this is if a CubeSat doesn't have to move in response to pointing. Say it simply has lasers pointing in a variety of directions and is in a nice stable orbit, it isn't going to move. It's just going to orbit the planet nice and stable. And so it can generate a nice stable laser beam. Now, if it does need to point, to turn, to do all the kinds of things that you do, if you do have to move around, well, in that case, we're looking at being able to maintain its position through communications with other objects. There's lots of different ways to handle this, and this is what the research is exploring, and it's cool to see the early days of a new idea. So the press conference, so Susie has the link to the entire conference. So CubeSats would be orienting itself the same way other things do, and this is by using gyroscopes to figure out their pointing and flywheels to do their pointing. It's all about conservation of momentum. Now, we should be starting any moment now. I'm going to go ahead and switch scenes to see what I can get. Things may become disjointed for a moment. Apologies as this occurs. So here we go with the transition over. Okay, so I'm in the process of trying to figure out why the full screen button on this doesn't work. And I believe we are now waiting for things to get started. I'm annoyed that we don't have full screen. Okay, working to sort everything in the background. Now, press conferences don't always start on time because there are herding of scientists that must occur. There is herding of scientists that must occur, as well as other innate craziness. So please bear with us while we work to sort and wait to see just how everything starts. I do have the ability to ask questions through chat, so if there's anything I can't answer, I will work to get it answered by folks who are there. Waiting impatiently. Herding scientists is like herding feral cats. It's not just questions, it's feral questions. Gladiator, I'm not sure how to say your name. We haven't sent out the Universe Sandbox keys yet because we haven't got them from the folks at Universe Sandbox. I need to chase those down. I'm so sorry. We're working to sort. I will make sure that you get them no matter what I have to do. Okay, yes, feral cats. And I'm not quite sure why my green screening decided it hates being on this setup more than it hates being on the other setup. Let me see what I can do to fix the green screening. So let me reload.
Of exoplanet discovery and understanding how solar systems like ours got here. This afternoon's briefing will also be on the subject of exoplanets. We'll be hearing from the NASA TESS team, Transiting Exoplanet Survey Satellite. So today's all about stars, star formation, and the planets around them. We have 4.5 presentations today. The first two, it's a tag team, Alexander Tielens from Leiden University in the Netherlands and Joan Schmeltz from the SOFIA and the University Space Research Association. They're going to talk about the disruption of Orion Molecular Cloud 1 by a massive star. I'll go ahead and name it. It's Theta 1 Orionis C, which if you don't look at the Orion Nebula with a telescope, you might not be familiar with, but if you do, you're very familiar with it. And its stellar wind is doing something to the star-forming cloud. Then we're going to have a presentation by Thomas Beatty from the University of Arizona on the universal presence of night-side clouds on hot Jupiters and what that implies about those particular strange class of planets. Then we're going to have two presentations involving discoveries by citizen scientists. Many of you know that citizens have been invited to participate in projects that have large amounts of data that need to be gone through, and that computers aren't necessarily the best way to go through that. So we have two planet discoveries by citizen scientists. The first talk will be by Adina Feinstein of the University of Chicago, a small transiting planet discovered by citizen scientists. And then Kevin Hardegree-Ullman from Caltech will talk about Spitzer spotting a sixth sub-Neptune in a system that was itself first explored by citizen scientists. So with that, I will turn it over to Xander Tielens. All right, so there you go.
I'll be talking about the disruption of the Orion Molecular Cloud core by the massive star Theta 1 OAC, the stellar wind of this massive star, and these are really SOFIA observations which are unique. And basically, feedback by massive stars is what regulates the interstellar medium and the formation and evolution of stars. And as feedback disrupts the cores in which new stars are formed, and it was always thought that this disruption mainly occurred through the ionization of the core, the ionization of the gas, which then flows away, or through supernova explosions. But what the SOFIA study has shown is that it is really the stellar wind during the early phases of the life of the star that disrupts these cores. Let me take you through this. These are three images, three infrared views of Orion. On the left, you see a Herschel image. The bluish emission is the interaction of the dust in this environment with the light from the stars. The reddish emission is the background molecular cloud where the stars are being formed. On the right, and this is due to the interaction of dust with the stellar radiation. On the right, you see the Spitzer image. That's a fluorescence by large molecules, also driven by the UV radiation from these massive stars. In the center, you see the new SOFIA data. This is the carbon plus fine structure line, which is the main cooling line of the gas that's being heated by these stars. And you see very similar structures in these regions, but actually these images do not full justice to the richness of the SOFIA data, because while the left and the right panel are mere images, the central one is actually 2 million spectra. And it's these 2 million spectra that give us the insight in what the kinetics is of the region and in what the three-dimensional structure of the region. And so let me take you through that. What you can do is use the Doppler information in the lines to get the velocity of the different structures in the region, and then use that to build up a 3D structure. And so on the left, you see the optical image with the well-known Orion Nebula, the hot plasma indivisible. On the right, you see the new SOFIA image. And here I have taken 3 different velocity slices in the 3 different colors. And particularly in the red here, you see this bubble that I'm going to talk about well outlined. And just to orient yourself, here I name some of these regions. The M42 is, of course, the well-known trapezium H2 region, M43, and to the north you see 1973, 1975, and 1977. It's this big bubble that's outlined particularly in the red on the right image that I will be talking about. And because we have this velocity information, we can actually build up a little movie where we go through the velocity profile, basically through and see these different structures appear. First, you see this bubble appearing. Then, in the middle, you see the region of the main interaction of the stars with the surrounding core. And then in the top, you saw the NGC 1973, 1975, 1977 appear. We go through this again, and if you now watch, you can see that this bubble is actually opening up. And it's this information that we can use to infer what is going on in this region and build up this 3D picture. And we find then that there is about 2,000 solar masses of material in this bubble that's expanding at about 13 kilometers per second, and it's all blown by this massive star, Theta 1 Ori C. Here's a cartoon of the region. You see in the center, you see the trapezium stars. The most massive star of this one has a strong stellar wind. That stellar wind is shocked, produces a very hot plasma, 2 million degree plasma. And it's the overpressure of this region that drives the expansion, and that sweeps up to the environment into this shell, into this expanding shell that is outlined here in red. And this expanding shell is being illuminated by the star, that's being heated by the star, and that emits in this carbon plus line. The bubble is mainly expanding towards the front, towards us, because in the back there is this dense molecular cloud. And this is a somewhat larger scale view of this region. You can recognize perhaps now the part of the Orion constellation. You see the belt stars, you see the 2 knees, the 2 shoulders are just off the image. And it's the lower ellipse that you should look at. That's the region where this bubble is. You recognize M42, M43, and the NGC regions outlined there. And you see the belt stars above it. And then the other part that you see here is this bright red emission region, which is called Barnard's Loop. And this is then a larger scale schematic of the region, just putting it all into perspective. You can, the bubble that's being blown by this massive star, well, at some point it will burst, it will release all the gases into the medium, and eventually one of the belt stars will go supernova. It will then sweep up all this loose stuff injected by these massive stars like Z1 OAC and move it off to the edges of this large bubble. This happened the last time was about a million years ago, and the red outline here, Barnard's loop, is the remnant of this material that's being swept up and now being moved towards the bubble edge. So if you want to think about it, the Theta 1 OAC are the movers who are packing everything in, and the supernovas are the ones who then transport it over large distances. And so in summary, the stellar wind from this massive star has blown this big bubble containing about 2,000 solar masses, which expands at 13 kilometers per second. That's about half of the mass in this star-forming core. Stellar winds really couple well to the molecular gas, and we have shown that it's the stellar winds that dominates the disruption of the molecular cloud core. At a later stage, the star will have moved off. It will go supernova, but by that time, the interaction with the mass-forming core is long past. My daughter gave birth to about a year and a half ago, and so my granddaughter is now approaching her terrible twos, and she's practicing her tantrums, and she's very good at that practicing. And basically what you can say is that this star is showing a tantrum, this young star is showing a tantrum, and throwing everything out of the birth sites in which it was formed and moving it around. And let me end with this slide because it shows Cornelia Papst. Cornelia is the student who's responsible for this work. She couldn't be here because of illness, but if you see my mouse move, that's only because she pulls the strings.
So I'd like to thank Rick for the extra 3 minutes because I'm the half of the 4.5 talks, and also Leslie Sage from Nature for helping put all of this together. And I get to talk about the fun stuff related to Xander's presentation. And this is something that we've been calling Orion's Dragon. And I'm just going to start with the same movie that Xander showed, except it zoomed in to the lower bubble. And it's also a slightly different color table. And the fun stuff about data cubes like this is you don't have to just look at velocity movies. You can do all sorts of different things with them. And this first one is the suggestion of Nick White. So we'll say thanks to Nick for this idea, where you have the position, the right ascension and declination, of course, on here. So this is the very front of the data cube. But going into the screen, you have velocity. So you can take the data cube and actually rotate it like this. And this is courtesy of our colleague Reese Taylor, who also couldn't be here, but is an old friend from Arecibo Observatory. And you can see this data cube rotating around. And we're about to come back to the very front where you see that Orion bubble that Xander talked about. And then now it's the velocity. The thin part is the velocity side of things. And again, back to the front. But as it comes around again, take a look at now as this feature sort of unfolds, that when we first saw it, we were all standing around my computer screen looking at it and said, hey, doesn't that look like a dragon? And everybody said, yeah, that's a dragon. And so there, right there, is the dragon. So it doesn't really appear very prominent from the front. But as now, when you're rotating around again, so you've got the head at the top, you've got this long tail, you've got some legs, And in the middle, right at the heart of the trapezium, where those trapezium stars are, where there's white, that's like the heart of the dragon and almost like a rib cage. So we've been playing around a little bit more with this dragon, thanks to Reese and his 3D rendering, because you don't just get to rotate it. You can, for example, zoom through it. So here's a rotation, and we're also zooming through the rib cage of the dragon. So all sorts of different ways that you can do these 3D renderings. So going into the heart of the rib cage and then coming back out again. And then everybody in the room should have a pair of red-green glasses on your chair. And the next and the last video is where you get to look at that and see if you can see Orion's dragon in 3D. So please don your glasses and take a look and see Orion in 3 dimensions. So this is, and hopefully somebody will get a picture of the press corps look with the glasses on, because Rick tells me that this might be a first, that we've never had these sort of glasses. So, and if you don't put your glasses on, you're going to be the one person in the picture that doesn't have them on. So we'll be able to point you out. Okay. So we have these because of the government shutdown. A lot of this information didn't make it onto nasa.gov, so there should be a piece of paper also on your chair with the web address for where these movies are available, because they are, as of this morning, not embargoed anymore, and all of you can download them and use them in whatever fashion you wish. So, thank you, everyone. Tight.
Save. All right, I was thinking while this was going, I liked, Rick, I like your analogy that this is the Super Bowl of astronomy. Except, as somebody pointed out, AAS isn't actually competitive, and that, as they said, since they're from Cleveland, they're also allowed to be here, which is another major difference. So, good morning, everyone. My name is Tom Beatty. I'm from the University of Arizona, and I'm going to tell you about a project that I've been working on with a bunch of other people that looking at hot Jupiter atmospheres and really looking at a delicate balance that we've been thinking about that has been occurring in hot Jupiter atmospheres for the last several years. And the results of this study is that instead of being in a delicate balance, that these atmospheres are really just lying on a slab of concrete, and there's no balancing act required at all. And that's because of, not to spoil it, the presence of night-side clouds on these objects. So we know from optical Hubble observations that clouds are present at the terminators and are sometimes present on the day sides of these objects. But things we did not know is how common are clouds. We have some sense that there's a variation from the Hubble observations. We don't know what the cloud properties are on the day and the night sides of these objects. And we don't have direct information about any of the clouds on the night sides at all, because Hubble just targets that green region at the dawn to dusk part of the planet. And finally, we didn't have a good sense of where this cloud formation had to be occurring on the planet. So if it occurred on the day side, only on the night side, exactly where it happened. And one way to get at this is to use something called phase curve observations. These are observations where we look at a planet for an entire orbit from start to finish, so you can see the day side rotate into view, the night side rotate into view. And these are really the main ways in which we can study the 3D climates of hot Jupiters. Eclipse observations, transmission observations, most of the observations you see of hot Jupiters are snapshots of the day side, of what's going on at dawn and dusk. Phase curves allow us to see these planets as 3D objects, as the entire globe and what's happening as you move in longitude across their surfaces. So as I mentioned, main result from the last few years of doing these observations has been that hotter planets seem to show very large temperature differences between their day and night side. As the planets get hotter, the temperature difference between the day and night side gets larger as well. And the balancing act that I mentioned at the beginning is that this has been thought about as competing thermal timescales. There's some sort of transport, how rapidly the planet moves heat from the day to the night, and a re-radiation timescale, how rapidly the planet dumps that heat back out into space. And the problem has been is that figuring out how that balancing act can work over 2,000 degrees worth of temperature has been a real interesting problem. And ostensibly, this should be telling us something about the dynamics of what's going on in the atmosphere, but it also can be hard to see how this applies to all these planets, from 1,000 degrees to 2,000 degrees. Okay, so that's some background. The specific observations that we did for this project is we observed a transiting brown dwarf called Kelt 1b. It's about 30 Jupiter masses. We got Spitzer phase curves. This is Kelt 1b going around its star in 2 different wavelengths. You can see I've cut off the transit sort of in the middle, but you can see there are 2 eclipses. That's as the Kelt 1b goes behind its star. And the rest of that modulation is the brightness changes on the surfaces of the planet, of the brown dwarf. The reason why we looked at this is that because it's a brown dwarf, Kelt 1b has very high pressure at the area that we're looking at, so we expected it to have effectively 0 day-night temperature difference. But it turns out that Kelt 1b is effectively exactly on the hot Jupiter trend, which was not what we were expecting to see. So what we did is we said, okay, well, these are the day-night temperature differences. What are happening with the actual temperatures, not only for this planet, but for all the hot Jupiters that we know about? And the weird thing that we saw was that it turns out that the temperature contrast is changing, not because everything's in perfect balance. The temperature contrast is changing because the day sides get hotter. The day sides are roughly clear. They're cloud-free. They get hotter as the planets get hotter. And the night sides are all consistent with being at the same temperature of 1,000 degrees. That is very weird. It's hard to see how this seesaw that's keeping everything in perfect balance is exactly poised such that all the planets, all the hot Jupiters we know, are at exactly 1,000 degrees on the night side. So our interpretation is that what this is night side clouds. We're seeing clouds at about 1,000 degrees on all these planets. They're all forming on the night sides of these planets, and that's what's clamping the temperature to 1,000 degrees. So instead of this balancing act, we have a competition between clear day sides and cloudy night sides on all hot Jupiters. On every single one that we've seen, it appears that there are night side clouds. Right. So instead of this delicate balancing act, this naturally explains this without having to do a lot of fine-tuning as just it's clouds. Right. So where are we at from these 3 questions I had for you at the beginning? Well, clouds appear to be present on all hot Jupiters on the night side. So every hot Jupiter that we've looked at in Spitzer appear to have clear day sides, roughly, and cloudy night sides. And there's some also transition, I haven't talked about it, but there has to be a sharp transition, a sharp point of cloud formation around dusk, and a sharp point where the clouds are burning off around dawn. And I can tell you a little bit more about that. That's a little bit of a more subtle point why that has to be. And finally, what are the cloud properties? So we don't have a very good idea from these data. What we have is a temperature. From that temperature, we can guess that there are probably some sort of silicate clouds. This is sort of like gritty sand that's been vaporized and is cloud form on the night side, or is some sort of manganese silicate clouds. It's all very weird stuff for on Earth, but for brown dwarfs and planets, these are pretty standard things, and we should have probably expected to see on these things. We see silicate clouds on a lot of brown dwarfs. But I will say that we are in the process of getting Hubble observations to try and measure the spectra of these clouds directly on the night side. So I don't have any results for that yet. I'm actually probably going to be working on that when I go back to Arizona next week. So you guys can all stay tuned and see where we are with that next spring. Thanks.
Hi, good morning. My name is Adina Feinstein. I'm a graduate student at the University of Chicago, and today I'm going to be talking to you about a literally cool world that citizen scientists helped us find. So as everybody knows, the NASA Kepler K2 mission was a huge success, identifying over 2,500 planet candidates over its entire mission lifetime. And the way that the Kepler mission worked, or K2 mission worked, is that every 3 months it would stare at a section of the sky, and it would collect the amount of light that we saw from the stars in this region over time, and then it would downlink the data to Earth. And so once we got what are called light curves, we would have to do some kind of systematics corrections, clean up the data a little bit before we started searching for planet transits. And as 21st century scientists, the first thing that we want to do is plug all of our data through algorithms to search for planet transits. And computers are really good at identifying transits, but sometimes they can get a little bit confused. So what I'm showing you in these 3 plots are examples of diagnostic plots that we look at to determine if something is a planet transit or not. And so the first plot that I'm showing you on the top here, the one that's labeled noise, we can see in the bottom right plot, this solid blue line represents what the computer thinks is a good transit fit for the data, but the points are very scattered around it. It doesn't really follow the trend. The second plot that I'm showing you, which is labeled binary stars, the data fits really well, but the shape and depth of the transit actually further identifies it as a star rather than a planet candidate. And the last plot is a potential planet transit. And so even though computers are really good at narrowing down the amount of light curves that we have to look at to identify planets, we still have to vet them by eye. And this is very, very tedious. And so we decided to outsource our data to the public, get people invested in identifying planets. And so through the Zooniverse citizen science platform, we have a program called Exoplanet Explorers. And we uploaded the light curves from Kepler, or from K2 campaign 0 through 15 onto this platform. And we showed the volunteers the diagnostic plots that I showed you on the previous slide. And we said, go forth and find us planets. And so for the system that I'm talking about today here, what exactly did they see? So again, this is the diagnostic plots that I showed you on a few slides ago. And we can see on the left here, this longer plot shows 3 very nice transits. So the solid red, the solid blue lines are the transit fits that the computer identified. And then in the bottom right, we see that the data really fits the transit well. And so citizen scientists got really excited about this system because given the initial stellar parameters that we had, they did some back of the envelope calculations and said, oh, this is a system that the planet is about 1 Earth radius, it's in the habitable zone, it's Earth 2.0, oh my gosh. And so they started this discussion thread that had about 14 participants and 140 comments, and that really caught our attention. And the reason why we didn't immediately follow up on the system is because when we first searched the light curve, which is shown here, we only saw 2 transits, which are identified by the red arrows. And in order to start the follow-up process for confirming planet candidates, we need at least 3 transits. But we saw on the previous diagnostic plot that there were 3. So what happened? When we look at Kepler or K2 data, we chop the beginning and the ends of the light curve off. So what I'm showing you here is the light curve that we saw, but it's not the entire light curve. The entire light curve looks like this. And there's a 3rd transit at the beginning that we initially chopped off. And so as we learned to better handle K2 systematic errors and learned to model them out instead of just chopping off the data, we uploaded these light curves to Exoplanet Explorers, and they found the 3rd transit for us. So without their help, we wouldn't have done the follow-up for this system. And so my co-intern at Goddard, McKenna Bristow, who's actually here today, she, as part of her summer research, also independently identified these 3 planet transits, and we started our follow-up observations. So the first thing that we did is we observed with the NASA Infrared Telescope Facility, which is shown in the right of the image of the telescopes. And we got spectra, or chemical fingerprints of the star, to better characterize stellar properties. And then with Keck, we did adaptive optics imaging, and we actually identified a binary companion. So in this plot, the 2 bright stars are the 2 stars in our system. And then we also identified an additional transit with Spitzer, and we got some more stellar parameters from the Gaia mission. And so all in all, I am very pleased to announce the discovery of K2288BB. And so the letters, I know it's kind of hard to say, the letters indicate what star the planet orbits. So the big B represents that it's the 2nd or fainter star in the system, so it's the brighter one in this image. And the lowercase b is just how we denote a new planet. And so the citizen scientists weren't totally off when they said Earth 2.0, except the radius is around 2.0 Earth radii, so it's twice the size of Earth. And it does indeed orbit in the habitable zone of the secondary stars. So it has an equilibrium temperature of around negative 47 degrees Celsius. And so all in all, we wouldn't have been able to find this really cool, literally, system without the help of citizen scientists. All the citizen scientists are co-authors on this publication that was released today on AJ. And I encourage anybody who is interested in continuing to help search for planet transits to continue to go back into the NASA K2 data. So this system was observed back in Campaign 4, which I forgot to mention earlier, which was observed in 2015, so it's older data. And so there's still so much that we have to search in the K2. And then now with the launch of TESS and the delivery of light curves from TESS, there's just going to be so much data out there that we won't be able to probably handle it ourselves. And it's going to be a great opportunity for citizen scientists to help us out. Thank you.
Thank you, everybody. Adina did a fantastic job introducing the Exoplanet Explorers program and the power of citizen science. I'm here to give you an update on a system that was discovered by citizen scientists, and we did some follow-up data to find out this system is even more interesting. And so I'm going to present K2-138. I'm Kevin Harder-Yeoman. I'm a postdoc at Caltech. So, as Adina mentioned, Kepler and K2 basically exploded the realm of exoplanets, found all sorts of candidates. We've now confirmed over 2,000, closer to 3,000 planets. And Kepler and K2 is great at finding planets, but sometimes we need to follow them up. With the K2 mission specifically, the duration of the mission doesn't allow us to confirm a lot of these longer period planets. Since K2 was staring at the same patch of sky for between 80 and 90 days for most of their campaigns, there are a lot of longer period objects that we don't necessarily have 3 transits to confirm a planet. So I'm showing on the bottom here just a typical light curve that you would see. So we use NASA's Spitzer Space Telescope to do lots of follow-up work for these planets. So last year at one of these press conferences, Dr. Jesse Christensen announced the first citizen science discovery with Exoplanet Explorers. There was a 5-planet system dubbed K2-138. The host star is a K-type star, so it's a little bit smaller than our sun. And there were 5 planets around this star. It's a relatively bright star, but it's kind of far away, so don't expect to go there anytime soon. The system architecture was also very interesting. All of these planets are, they have sizes between that of Earth and Neptune, so unlike anything in our own solar system. So that was really neat. They also orbit in a near 3-2 resonance. So what that means is that for the inner planet, every 3 times it orbits, the next planet out orbits the host star twice. So this is the longest undisturbed near 3-2 resonance system that we've ever discovered. So that was already interesting. But in the K2 data, there was evidence for a 6th planet, but we only had 2 transits. So what we did was we submitted a Spitzer Director Discretionary Time proposal to try and go find this potential 6th planet in this very exciting system. And lo and behold, we have a transit exactly where we predicted it would be. So here's a Spitzer light curve. The raw data points are in gray. The binned data points, just to make it easier to see, are in the red. And then there's the blue line, which shows the transit model. And then the bottom is just the residual from subtracting the data and model, and it's perfectly flat. So it's a really good fit. So here's our new view of the system. We have 6 planets in this system. The inner planets actually orbit really close to the star. So the innermost planet orbits every 2.5 days, and the previous furthest out planet orbited every roughly 13 days. This planet that we confirmed orbits at 42 days. So 1 year for this planet is 42 days, which is why we were not able to find a third transit in the K2 data, because it only spanned about 83 days for this campaign. So, looking at the system architecture now, this planet is much further out. However, it's still consistent with the other planets. It's still a sub-Neptune. It's very close to the size of Neptune, but it's still within the range of not being like anything else we have in our own solar system. However, the difference is you'll see that there are nice spacings, and those spacings get a little bit increasing for each orbit, but then there's this whopping further out planet. Question is, could there be more planets in the gap that are either too small to be able to detect with our current technology, or could they be just off the plane of orbiting in front of the star? So there could be more planets. We need to use other methods to potentially tease that out. But the system is very interesting. As I mentioned, that it's in a near 3-2 orbital resonance, and this outer planet, if you continue the chain, and if there were 2 more planets sort of in there, in between planet F and G, it is fairly close to this continuing this 3-2 resonance chain, but it's off by a little bit. But when nature gives you something nearly pristine like this, why not make a music video? So I'm going to show you a video of this system put to music, and hopefully, I don't know, we're not hearing it. There we go. So those with some musical background or very good hearing probably noticed when you saw the disc there that it seemed like it was in tune. This could possibly explain some of the formation mechanism and what we see today. So you saw that the timelines went from birth to today. So here's a graphical depiction of that. The inner planets we put at a 3-2 resonance to start out with. Potentially this system started out in resonance, and once we dissipated the disk to conserve angular momentum, that had to shift slightly out of resonance. So when we put that to music, that's what we saw. And so many thanks to Matt Russo and his team for sort of helping us visualize that and in a really cool manner. So, in summary, we have been able to confirm a 6th planet for K2138, the first citizen science system that was discovered with the Exoplanet Explorers project on Zooniverse. This is only the 9th exoplanet system with 6 or more planets. So, there's a growing population of many planet systems, and hopefully we'll get a lot more data. There's an ongoing campaign to measure masses of these planets, so hopefully that will tell us about the density and then composition, and maybe there are more planets hiding either in the gap between F and G or beyond this 6th planet. So thank you.
Thank you all very much. Well, this was a milestone in the history of AAS press conferences because we had 3D stereo movies and the music of the spheres. As you can tell, this isn't the 20th century anymore. So we're going to take some questions from the room and then questions from the internet. I need somebody to carry around one of our handheld mics. Can I get a PIO volunteer or something? Thanks a lot. So if you have questions from here in the room, please raise your hand and wait for the microphone so that the folks on the webcast can hear you ask your question. Okay, questions? All right, we'll have Alan Boyle down here. give your name and your affiliation.
Hi, I'm Alan Boyle with GeekWire. This is
It's,
on.
here it
you hear
comes.
me?
There it
we
is.
go. I'm Alan Boyle with GeekWire. I wanted to ask Adina, you had some information about the habitable zone. Could you kind of go through that again? I think you mentioned what the expected temperature was, but maybe the temperature gets warmer if there's an assumption of an atmosphere or something like that.
Yeah, so the habitable zone is defined as a region around a star where liquid water could potentially exist on the surface. But yeah, again, as you said, with an atmosphere, it could potentially raise the surface temperature of the planet. We don't know anything about the atmospheric composition of the planet, so the temperature that we're giving is just a really rough estimate. And even though it is in the habitable zone, it doesn't necessarily mean that it is a habitable planet.
Did you say it was minus 47 degrees?
Celsius, yeah.
Okay, we have one way over here. And by the way, this guy who's about to ask the question, he's the one who came up with Super Bowl of astronomy, not
Thank
me.
you for that. That's my one accomplishment. Steve Marin, freelance for Thomas Beatty. You may have mentioned it and I missed it. If you would clarify, are these hot Jupiters all in synchronous rotation? In other words, is the far side always the night side?
That's actually a very interesting point, Steve. So the short answer is yes, but that's the bulk angular momentum of the planet, right? So the atmosphere itself is rotating on top of that. So there is a lot of transport from the day to the night side in terms of the atmosphere.
Venus does that too, right? Where the atmosphere is rotating at a very different rate than the planet underneath it.
Even the Earth does it.
Yeah, right. Okay. Okay, we have one back here.
Christine Pulliam, STSCI. Quick question for Kevin. Of the 6 planet system, are any of them in the habitable zone, or are they all too close?
That's a very good question. They are all too close. The inner planet on the first diagram that I showed, all the innermost planets orbit their orbits are closer than 0.1 AU, so a tenth of the distance between the star and Earth. So the outermost planet orbits every 42 days. That's still less than half of the orbital period of Mercury. And this star is almost the size of our sun, so it's definitely not habitable.
Have we got any questions on the webcast? Okay, we'll take a couple of those.
All right, we have a question for Dr. Beatty from Monica Young at Sky and Telescope. She wonders if you could elaborate a bit more about your comment that there's a more subtle point to be made as to why clouds burn off at dawn and form at dusk.
Sure. So this is something I didn't, didn't quite get to. So what we see in the observations is we see the entire disk of the planet integrated into a single point. So we see the disk integrated flux from all these planets. You can try and back out what the underlying surface temperatures have to be to generate that. If there is no sharp transition at dawn and dusk from the clouds forming, the night side temperatures have to be negative. The night side has to be putting out negative emission for us to match the data. Since that can't be happening, our conclusion was that there has to be some sort of sharp transition, which looks exactly like what you would expect from cloud formation occurring.
Anything else? Okay. Any more in here? Well, if this is your first AAS press conference, you may not know that I always have questions. And I haven't figured out if it's because I'm listening particularly carefully or if I'm just really thick. But in any case, I have questions for everybody. I'll start with Xander and Joan. First of all, Orion is often considered sort of the prototype star formation region. Now, you've gotten a look at it where you're seeing structural detail, velocity detail, that's much higher resolution and much more detailed than you are able to see in most other regions. I'm wondering, do you anticipate, based on what you've seen there, that other star-forming regions will have similar structures, or is there something about the Orion region that might make this one an exceptional case?
No, I expect that that all massive stars have these kind of stellar winds.
Mm-hmm.
We know that very well, and they all blow these kind of bubbles. It's just that this is very close or very nearby that we can really study it in great detail and see things. But we do have a new program on Sophia approved, where we will be studying another 10 objects like Orion, regions of massive star formation over the coming 2 years.
Are you going to go to the Southern Hemisphere, for example, to look at some of the big ones down there? Yeah, great. Okay. So, Joan, those movies were a lot of fun. I'm wondering what scientific insights you may have drawn from them that weren't already apparent to the team from looking at them in the various slices of data. You know, what is it about the animations or those particular views that, what did you learn from that?
So the movie that Xander showed at the very beginning is one of the ones I've looked at so many times that it's frozen my computer. And one of the things that comes up at the very end of that movie is a filament, a twisted filament that is an extension of the Orion bar that you don't see any other way. And it almost begs the question, can you actually model that with simple hydrodynamics, or do you need magnetohydrodynamics to do it? And hopefully we'll be able to, Xander's result, or Xander's paper that just came out this morning doesn't really address that filament, but hopefully some of his team will be working on that in future. So that's just one of the things that comes out of the videos and shows sort of the power of the spectroscopy.
By the way, you mentioned when you were speaking earlier, you mentioned nature, and I forgot to mention nature, so I want to do that now. And thanks again to Leslie Sage and his team. Xander's paper went online just before the briefing, and so that's now available. And I always appreciate it when there's something in Press at Nature that's being presented at the AAS meeting, and we're able to coordinate so that the paper comes out and we can have the briefing, and you guys can dive into the story. So thanks again for that. A question for Dr. Beatty. Yeah, so you're talking about hot Jupiters, and you're talking about clouds. Now, when we think of Jupiter, we think of a planet that's essentially clouds all the way down. So what I'm trying to imagine is, what would one of these systems look like in the daytime with a quote-unquote clear or cloud-free atmosphere? Can you help us visualize how that would look compared to an actual Jupiter, the one we know?
Yeah, that's actually a very interesting question, Rick, that I've sort of been kicking around in my head as I was writing the paper. So the thing about it is, even when I said that these atmospheres, they're clear day sides, that doesn't mean we can see all the way into the interior. In the same way that the sky on Earth is blue because of scattering processes in the atmosphere, the sky would look, you would have a little bit of scudding clouds coming over from the night side. You'd have a little bit forming right at dusk, but the day side would just, I think, sort of look hazy. I'm not entirely sure about this, but I think it's sort of hazy, maybe a little bit blue from the Rayleigh scattering, and then the night would have these clouds forming and would be much more opaque on the night side.
I don't want to hog the microphone. Are there any other questions from here in the room right now? How about online? Okay, take one there.
We have a question from Pamela Gay at Astronomy Cast, and this question is for Joan. What software did you use for the visualization, and is this something that others can use as well?
The software is specialized, and it's actually written by Reese Taylor. So he is the person who has all of that available, and that's why we reached out to him to do these 3D renderings. So it's not generally available software that we've used.
And where is Reese Taylor? Is he at Sophia?
He's in the Czech Republic. And again, sorry for this, but if you're in the room, the paper on your chair gives a little bit more detail about the 3D renderings. And apologies to everyone who's not in the room, but this is we're sort of a victim of the government shutdown that we could not put this release up on NASA.gov. So maybe we can maybe after.
I can post it on the press kit.
Yeah, so
on the AAS website.
We should. I'll just make sure that that's okay, and we can do that after the fact.
Excellent. Anything else, Carrie? Okay, I'll continue down the line. We have a few more minutes. So a question for Adina. You mentioned that you, by default, you chop off the beginning and the end of the light curves before it goes to the citizen scientists, and you alluded to some systematic errors. Can you elaborate on that a little bit more?
Yeah, so after the 2 reaction wheels of Kepler failed, they reoriented the spacecraft to start the K2 mission. And the reorientation actually caused some minor changes in the spacecraft itself, like physical changes and also changes in the electronics. And so originally we didn't really know how to deal with that, how to correct for that. And so we just chopped it off. But then later on we learned how to model and subtract it out.
Okay, okay. So the data is all recoverable?
Yeah.
Okay. And I had a question for Kevin, but at the very end of your talk, you answered it. I was trying to understand how this new planet might fit in with those 3-2 resonances. So you answered that, so thank you. Any further questions here online? All right. Well, then I'd like to thank our speakers again. And this is monumental because we often worry that we're going to have technical difficulties or other difficulties in the first briefing of a big meeting like this, but everything went perfectly according to plan. So I thank everybody who had a hand in making that happen. So the next briefing will be this afternoon at 2:15 p.m. And that one is on early science from TESS. And we will have this is one of the few briefings that was actually affected by the shutdown. So one of our NASA people wasn't able to come, but we'll have 5 presentations from 4 people on new exoplanet work and other work from the TESS mission. So I look forward to seeing you back here at 2:15 Pacific time, and we'll be webcasting that again as well. Thanks all for your attendance, and we'll see you later.
Sorry about that. Yeah, I'm really good about being muted. So sorry. Thank you all for your patience. So thank you all for being here. We are going to do everything we can to bring you all of these press conferences this week. And now that we have all the information on this week's schedule, hopefully it will be easier to prep for some of these sessions. Now, one of the things that we are up against is, in many cases, the reason these press conferences are scheduled at 15 minutes past the hour is because the embargoes end at the top of the hour. So with that particular press conference, we had the nature embargo ending at 10 a.m. Pacific. They went live with the press conference at 10:15. That was not enough time for me to access and download and read and absorb the paper, especially since I was already streaming. Yeah, so here's where things seem to be going. Anyways, we will be back later on today, and hopefully all will be going well with this world. And do you guys have any questions before we break? As always, my name is Dr. Pamela Gay. I am coming to you from the Planetary Science Institute, and this stream is done in collaboration. Thank you, Trucker Kev. This stream is done in collaboration with Youngstown State University. We will be bringing Annie Wilson, who is live on the scene, here later, and look forward to sharing with you all that is new and awesome. Thank you, Prof. Melko, for the subscription. Thank you so very, very much. This stream is so Guildster is asking, are they using AI to find possible transits in the data? It's not so much AI or machine learning as they use a combination of algorithms that are essentially looking to see if the light curve fits known patterns. There's no training set. It just either fits or doesn't. And they are also using citizen scientists. This is a Zooniverse project. I was co-founder of Zooniverse before being asked to split off and form CosmoQuest by a variety of the planetary science missions that we work with. Yeah, stuff and things. There will be more coverage at 5:15 Eastern. And we are sustained by your subscriptions, and every bit really matters. Please give us a follow to find out when we go live, and we will do our best to put science in your brains, bringing you daily news with the Daily Space, running most Mondays through Fridays at 1 p.m. Eastern. That is math. That is 10 a.m. Pacific, 6 p.m. London time. We also bring you live events such as launches, landings, press conferences from the world of astronomy and space science. We have Astro Office Hours with myself and Annie Wilson, and we are always looking for new programs to add to put more science into your brain. So thank you for being here, and thank you for all your support. And I'm apparently creeping Annie out with her timing and coincidences. So we'll be back later today, wherever you are in the world. You can follow everything we do on Twitter. You can keep up to date with what is coming on normally at our website, but we're in the process of massive revisions right now. So stay tuned to see what is new and exciting. We'll bring it to you as soon as things are ready. We are able to make these improvements because of you. And just one more time, I want to thank all of you for what you've done to make everything we do possible. So thank you for supporting us, and I'll see you on the other side. Bye-bye.